When you look at the night sky, you're seeing a story that began long before Earth existed. Every time you lift your eyes toward the stars, you are not simply looking at sparkling points of light. You are seeing light that has traveled for billions of years, crossing a universe that expanded as it moved. You are seeing patterns shaped by invisible forces that have been at work since the birth of everything. You are watching the past, imprinted in light. What is even more astonishing is this. Many of the atoms inside your body, atoms that allow you to breathe, think, feel, were created by stars that died long before Earth formed. Every molecule of water inside you is older than the sun. Every particle of calcium in your bones was forged in the fire of a star that exploded millions or even billions of years ago. Today, I invite you to hear the full story that unites all these facts. A story about how, from a state in which there was no space, no time, no light, and no matter, the universe emerged, giving rise to everything familiar to you, and even to things you will never see. Chapter 1. The most mysterious question. What was before the beginning? Almost everyone who hears about the Big Bang for the first time asks the same question. What was before it? It feels natural, logical. But this question breaks the very foundation of reality as we understand it. Modern physics tells us, before the Big Bang, time did not exist. If time does not exist, then concepts such as before, after, and later are impossible. Time is not an external river flowing on its own. Time appeared together with space, energy, and matter. This is why the question of what existed before is similar to asking what lies north of the North Pole. Yet science does not stop at a formal answer. Researchers explore hypotheses, each one more surprising than the last. First hypothesis, the multiverse. Our Big Bang may be only one among countless others. There may be universes with different laws of physics, different kinds of matter, different flows of time. We might be only a single bubble in a vast, boiling cosmic ocean. Second hypothesis, cyclic evolution. The universe might endlessly repeat a cycle of expansion, cooling, collapse, and rebirth. In that case, our Big Bang would simply be another heartbeat in an eternal cosmic pulse. Third hypothesis, collision of higher dimensional membranes. According to string theory, our universe is a three-dimensional membrane floating in a space with more than 3 dimensions. A collision between membranes could release enough energy to create a universe. Fourth hypothesis, quantum emergence from the vacuum. The quantum vacuum is not empty. It is a sea of energy. Within it, spontaneous fluctuations may give birth to entire universes. We do not know which idea is closest to the truth. But one thing is clear. The Big Bang is not just an explosion. It is a boundary beyond which reality becomes deeper than anything you are accustomed to.
Chapter 2. The first moments, physics we do not yet understand. Imagine a state where density climbs toward infinity, temperature is unimaginably high, and space and time are so distorted that our familiar laws stop working. This is the moment of the universe's birth. We cannot describe it in detail. Our theories collapse in the attempt. We call this moment the Planck epoch, but the name is simply a label hiding the fact that we understand almost nothing about that phase. Yet shortly afterward, the universe enters territory where physics begins to operate. And here, the true cosmic drama begins. Chapter 3. Inflation, growth beyond imagination. Roughly 1/10 million trillionth of a second after the universe appeared, something extraordinary happened. The universe began to expand so rapidly that its size increased by 10 to the 78th power times. This event is called cosmic inflation. To imagine it, you would need to picture a single atom expanding to a size larger than the entire observable universe. Inflation is the fastest growth that has ever occurred. It solves several deep cosmic mysteries. Why is the universe so smooth? The temperature of the cosmic microwave background is nearly identical in all directions. Inflation stretched a small, uniform region into a vast one, smoothing everything out. Why is the universe almost perfectly flat? Inflation spread out space the way blowing up a balloon smooths its surface. Where did the seeds of galaxies come from? On the quantum level, fields fluctuate constantly. Inflation magnified these microscopic fluctuations to scales large enough to form future galaxies. In a sense, the location of every galaxy, including the Milky Way, was set by random quantum vibrations. Your existence at its deepest level is the result of a tiny tremor in a primordial field.
Chapter 4. The First Seconds, the Birth of Matter. When inflation ended, the universe was filled with an extremely hot soup of particles: quarks, antiquarks, gluons, leptons, neutrinos, photons. The temperature was so high that particles and antiparticles continuously appeared and annihilated each other. After 1/1,000,000th of a second, quarks joined into protons and neutrons, the basic building blocks of atoms. After 1 second, neutrinos decoupled from matter and began to travel freely through space. They are still moving through you right now, billions of them every second, without leaving a trace. After several minutes, primordial nucleosynthesis began. The universe formed the first atomic nuclei: hydrogen, helium, a little lithium. These simple elements make up almost all ordinary matter in the universe. Their observed proportions match the predictions of the Big Bang theory with remarkable precision, one of its strongest confirmations. Chapter 5. 380,000 years later, the universe becomes transparent. Until this moment, light could not travel freely. Electrons and nuclei formed a dense plasma. Photons bounced around endlessly, unable to escape. But when the temperature dropped to around 3,000 degrees, electrons joined with nuclei to form neutral atoms. Light was set free for the first time. This ancient radiation, still traveling today, is known as the cosmic microwave background. It fills all of space. The Planck satellite revealed that its temperature is almost uniform, with tiny variations. These tiny fluctuations are the seeds of galaxies. When you look at a map of the cosmic microwave background, you are literally looking at the infancy of the universe. Chapter 6. The Era of Darkness, when the universe was empty and silent. After the birth of atoms, a long cosmic night began. There were no stars, no galaxies, no light. Only vast clouds of hydrogen and helium floated in the void. Gravity slowly pulled matter into denser regions. Hundreds of millions of years passed before the first light returned. If you could have traveled to that time, you would have seen complete darkness in every direction. Yet hidden within that darkness were processes that would transform the entire cosmos. Chapter 7. The First Stars, Giants that Turned on the Cosmic Lights. Around 100 million years after the beginning, the universe took its next major step. The first stars were born, enormous, brilliant, unstable. Many were tens or even hundreds of times more massive than our sun. They lived only a few million years, but their importance cannot be overstated. These stars created the first heavy elements: carbon, oxygen, silicon, iron. These elements would later become the building blocks of planets and the foundations of life. You literally carry within your body the ashes of ancient stars. Chapter 8. Dark Matter, the invisible foundation beneath every galaxy.
When astronomers measured how stars move within galaxies, they found something puzzling. The stars were orbited too fast, as though held by an unseen mass. This mysterious substance is called dark matter. Dark matter does not emit light, does not interact with electromagnetic forces, but has mass. It forms a gravitational framework around which galaxies are built. Without dark matter, the Milky Way would not exist, the Sun would not exist, Earth would never have formed, and life would be impossible. Dark matter is the unseen architect of the cosmos. Chapter 9. Dark energy, the force stretching space itself. At the end of the 20th century, scientists made an astonishing discovery. The expansion of the universe is speeding up. This means that space is filled with a mysterious substance, dark energy, which is invisible, cannot be detected in laboratories, but shapes the fate of the entire universe. Dark energy makes up about 70% of everything that exists. We understand less about it than about any other physical phenomenon. Yet, it determines what the future of the cosmos will be. Готов. Продолжаю сразу. Ни одного слова вне текста, только продолжение перевода. Ниже часть вторая английского перевода. Тон тот же, дружелюбный, научно-популярный. Обращение на «ю». Все числа прописью. Никаких сокращений. Chapter 10. The major puzzles of modern cosmology. Even though the Big Bang model explains an enormous number of observations, science still faces deep and serious challenges. First puzzle: different measurements of the expansion rate. Different scientific methods give conflicting values for the rate at which the universe expands. The disagreement is too large to be a coincidence. This may mean that something fundamental is missing from our current understanding. Second puzzle: galaxies that formed too early. New observations from powerful telescopes reveal massive, complex galaxies that existed only a few 100 million years after the beginning. According to standard calculations, such galaxies should not have had enough time to grow. Third puzzle: the disappearance of antimatter. Why did ordinary matter win? Theory predicts that matter and antimatter should have been created in equal amounts. Yet antimatter almost entirely vanished. Fourth puzzle: the unknown nature of dark matter. Scientists have searched for dark matter for decades using many methods. Not a single candidate particle has been confirmed. Fifth puzzle: what exactly is dark energy? We do not know its origin, its physical nature, or whether it changes over time. It may hold the key to a deeper theory of the universe. Each of these mysteries has the potential to reshape physics in profound ways. Chapter 11. The Future of the Universe. 3 Possible Endings. There are 3 leading scenarios for how the story of the cosmos might unfold. First scenario: the Great Freeze. This is considered the most likely. The expansion of the universe continues forever. Galaxies drift farther and farther apart. Stars burn out one by one. The cosmos eventually becomes a cold, dark, and silent place. Second scenario: the Great Rip. If the strength of dark energy increases over time, it could tear apart galaxies, stars, planets, atoms, and eventually the very fabric of space. Third scenario: the Great Collapse. If the effect of dark energy weakens or reverses, expansion could stop and give way to contraction. The universe might shrink until it reaches an extremely dense state once again. We do not yet know which path will be taken. The answer depends on cosmic forces that are still not understood. Chapter 12. Why this is your story. When you hear the story of the Big Bang, you are hearing the story of your own origin. The atoms in your body were born in stars. The chemical elements that make you who you are were forged billions of years ago. You are part of the universe. You are one of the ways the universe explores and understands itself. The Big Bang is not only the beginning of space and time. It is the beginning of the chain of events that led to you. Your bones are written in the language of ancient stars. Your breath contains atoms older than the sun. Your existence is woven into the same fabric as galaxies and nebulae. The universe is not finished. It continues to evolve, and you are one of its chapters.
As you move deeper into the story of the universe, you eventually discover that the Big Bang, for all its power and clarity, is only the beginning of a far stranger and richer landscape than it first appears. For many decades, scientists believed that explaining the expansion, the formation of elements, and the glow of the cosmic microwave background was enough. But as new telescopes opened new windows, and as mathematics advanced into realms unimagined by early cosmologists, the question slowly shifted from how did the universe begin to why did it begin this way and not some other way? This shift opened the door to hypotheses far more daring than anything in the standard Big Bang picture. And now, as you follow this unfolding story, you will find that the origins of the universe might lie in realms beyond this universe itself. One idea, fascinating in its simplicity and overwhelming in its scale, is the concept of eternal inflation. If normal inflation caused the young universe to expand at unimaginable speed, eternal inflation proposes that inflation did not stop everywhere at once. Instead, in countless regions, the inflationary field continued expanding endlessly, driven by quantum fluctuations that prevented it from settling. In such a picture, our universe is only one bubble in a vast cosmic sea, where bubbles of spacetime constantly appear, grow, and detach from one another. Inside each bubble, conditions are different. Some bubbles may expand rapidly, others slowly. Some may contain 4 spatial dimensions instead of 3. Some may have entirely different particles or different strengths of gravity or no chemistry as you understand it at all. In this vision, what you call the universe is simply your local region, a tiny island in a cosmic archipelago stretching beyond any horizon you could ever observe. But eternal inflation raises another question. If there are endless bubbles, why does your bubble have the laws of physics that it has? Why is gravity weaker than electromagnetism by a staggering factor? Why do atoms form the way they do? Why does matter outweigh antimatter by the slightest margin that makes life possible? Here another idea enters, the concept of a cosmic landscape. According to some versions of string theory, the fundamental equations describing reality allow for an enormous number of possible environments, perhaps more than 10 to the power of 500. Each environment, or vacuum state, corresponds to a different way that the extra dimensions could be curled up, leading to different physical laws. If this landscape is real, then eternal inflation acts like a cosmic explorer, generating universes that sample different points on the landscape. Your universe might simply be one of the locations where the laws happen to allow long-lived stars, stable atoms, and the slow unfolding of complexity. You are here not because the universe was designed with life in mind, but because only a universe with such precise parameters could produce observers who ask questions at all.
This is known as the anthropic principle, a concept that is often misunderstood but deeply powerful. It does not claim that the universe was made for you, but instead that observers can only exist in universes compatible with their existence. In this view, the universe is not fine-tuned for life. Life is fine-tuned for the universe it finds itself in. But perhaps this entire landscape of possibilities is only a first step. Another hypothesis proposes that the Big Bang was not a beginning but a transition. According to loop quantum cosmology, a field attempting to unify general relativity and quantum mechanics, the Big Bang singularity is replaced with a quantum bounce. In this model, the universe before the bounce was contracting, growing denser and hotter until quantum gravity prevented further collapse and triggered a rebound. The universe then expanded outward, creating the world you observe today. If this is true, then the Big Bang was not an explosion from nothing, but a moment when the universe passed through a minimum size and reverse direction. You would be living in a cosmos that oscillates, not endlessly, but in cycles determined by quantum geometry. The laws of physics you know might be echoes of an earlier cosmic era, imprinted like faint fingerprints on the background radiation. Yet another idea, proposed by the physicist Roger Penrose, is that the universe goes through cycles not in space, but in scale. In his conformal cyclic cosmology, the universe grows larger and more dilute for trillions upon trillions of years. Eventually, as black holes evaporate and all particles lose mass, there is no meaningful difference between one moment and another. In that state where scale becomes irrelevant, the universe can be mathematically reshaped into the beginning of a new one. In this vision, the distant future of one universe becomes the Big Bang of the next. Penrose has even suggested that subtle patterns in the cosmic microwave background may contain hints of events from a pre-existing universe, perhaps the final evaporations of black holes that lived in a previous aeon. If this were true, then you would be living in a universe with memories, faint scars carried across unimaginable stretches of time. There is also the mirror universe hypothesis. In this model, your universe is paired with another universe that exists on the opposite side of the Big Bang. In that mirror universe, time flows in the opposite direction relative to you. That universe would not be a reflection in space, but a reflection in temporal symmetry. In that world, entropy would increase away from the Big Bang just as it does in your world, but in the opposite direction. From the viewpoint of an observer inside that universe, everything would appear completely normal. But from your perspective, their entire arrow of time would run backwards. This idea attempts to answer one of the most profound questions in cosmology. Why does time move forward at all? Why does entropy increase? Perhaps the Big Bang created two universes, each with its own direction of time, balancing one another like positive and negative charges. This mirror time hypothesis offers a surprising bonus. It provides a natural explanation for the dominance of matter over antimatter. If your universe contains more matter, the mirror universe would contain more antimatter, balancing the cosmos as a whole. But even this does not exhaust the landscape of possibilities. Some researchers propose that spacetime itself may not be fundamental. Instead, it may be an emergent phenomenon, arising from networks of quantum information woven together at unimaginably small scales. In such models, the Big Bang would not be the beginning of space, but the moment when a deeper informational structure crossed a threshold and began behaving like classical spacetime. The universe, in this case, is the surface behavior of a far richer underlying reality. If that is true, then your questions about the beginning are shaped by your limited view of a deeper informational cosmos. The Big Bang would be like the moment ice forms from liquid water. The molecules existed before the ice, but the solid structure emerged only after conditions changed in the right way. In this analogy, the Big Bang is not the birth of existence, but the crystallization of a particular phase of reality. The question then becomes, what came before the crystallization? And does that deeper reality still exist underneath everything you see? Still, other ideas suggest that the universe was born from quantum tunneling, a process similar to the way particles can appear on the other side of an energy barrier without ever passing through it. In these models, your universe spontaneously tunneled into existence from a state with no classical spacetime at all. It popped into being like a bubble, appearing within a quantum vacuum, carrying with it the seeds of inflation that shaped its early moments. This quantum tunneling idea leads to a profound possibility. Perhaps universes appear all the time, not through intentional cause, but as natural expressions of quantum laws. If so, the existence of the universe is not a miracle, but an expected outcome of reality's deepest rules. But even the quantum vacuum idea raises a deeper puzzle. Why do quantum laws exist in the first place? What gives rise to the probabilities, fields, and structures that allow universes to appear? Does mathematics itself have an existence independent of physical reality? This question pushes cosmology into territory once reserved for philosophy. But in modern science, the boundary between physics and metaphysics is thinner than ever. You now stand at the edge of a cosmic cliff. Below you lies the familiar Big Bang theory. Above you rise mountains of deeper possibilities. With every new telescope, every new particle experiment, every new mathematical insight, the view becomes wider, stranger, more intricate. And still, the greatest mystery remains. Why is there anything at all rather than nothing?
If you follow the question of why is there something rather than nothing deeper and deeper, you eventually discover that the very words something and nothing are far more complex than they first appear. In everyday language, nothing means emptiness, absence, a quiet void without form or content. But in modern physics, nothing becomes a highly structured idea, one that contains potential, energy, laws, and possibilities. This leads to one of the most fascinating hypotheses in cosmology, the idea that the universe may originate from a state in which spacetime, particles, and forces did not yet exist, but the laws of mathematics did. In this picture, the universe comes into being not out of physical material, but out of a foundation of mathematical consistency. That is, if certain mathematical structures are possible, then universes may arise that reflect those structures. Some scientists, like the cosmologist Max Tegmark, propose that mathematics is not merely a tool for describing reality, it is reality. According to this view, every consistent mathematical structure corresponds to a physical universe. Your universe is simply one such structure, with its particular symmetries and constants forming a coherent pattern. In this idea of a mathematical multiverse, the Big Bang is not an explosion, but the manifestation of a mathematical object coming into physical existence. This is bold, but it addresses a deep mystery. Why are the laws of physics mathematically beautiful? Why do differential equations, symmetries, and group structures govern everything from quarks to galaxies? Why should reality follow rules that can be written with symbols? Perhaps it is because the rules came first. Other researchers suggest that the universe is not purely mathematical, but informational. They argue that space-time, matter, and energy emerge from information itself. According to this framework, the universe at its root consists of interactions, relationships, and bits of data. Physical reality becomes a kind of computation carried out on a vast and ancient cosmic substrate. If this is the case, then the Big Bang is not the origin of matter, but the moment a giant informational system shifted into a new state, igniting the rules that would eventually create stars, galaxies, and you. The earliest moments of the universe becomes a phase transition, a shift from one kind of informational structure to another. You can imagine it like the moment liquid water freezes into ice. Before freezing, the molecules move freely. After freezing, they lock into a rigid crystal pattern. The Big Bang, in this analogy, is the moment when the underlying informational field froze into the space-time you inhabit. This raises a surprising and profound question. Does the informational field still exist beneath space-time? And if so, can the universe undergo other transitions in the far future, creating physics that look nothing like the laws you know today? As you explore these questions, you encounter another concept, the holographic principle. This idea proposes that the three-dimensional world you experience is not fundamental.
Instead, it may be the projection of information encoded on a two-dimensional boundary far removed from your everyday perception. In this view, the universe resembles a cosmic hologram, where the true source of reality lies on a distant surface and everything you see is a lower dimensional representation.
This may sound abstract, but strong hints of the holographic principle appear in black hole physics. A black hole has a surface called the event horizon, and the amount of information it can contain is proportional not to its volume, but to the area of this surface. This fact shocked physicists because it suggests that the three-dimensional interior of the black hole is completely described by a two-dimensional boundary. If this is true for black holes, could it also be true for the entire universe? Some researchers believe so. If the universe began with a Big Bang that acted as a kind of cosmic horizon, then your reality might be encoded on a distant boundary you can never reach. The three-dimensional world you navigate would be an emergent illusion arising from deeper hidden rules. In this view, the Big Bang becomes not the birth of space, but the activation of the holographic surface that encodes everything you see. But now, consider an even stranger possibility. What if the universe did not begin at the Big Bang at all? What if the Big Bang is the boundary inside our universe, not its true beginning? This thought leads to the ekpyrotic model, a cosmological idea emerging from higher dimensional physics. In this framework, our universe is a three-dimensional membrane floating within a higher dimensional space. A parallel membrane exists nearby, invisible to us. Over immense epochs, these membranes drift and eventually collide. The energy released in such a collision appears inside the membranes as a hot, dense state, a Big Bang. If this idea is correct, then your universe was born from the collision of worlds. The heat of the early cosmos reflects the moment two vast, invisible surfaces crash together in higher dimensional space. And because these membranes continue moving, another collision could occur in the distant future, leading to cycles of cosmic creation. In this ekpyrotic vision, the universe does not arise from nothing, but from interactions between structures larger and more complex than anything inside spacetime. Yet even this does not exhaust the possibilities. A different set of ideas comes from quantum gravity, which attempts to merge Einstein's relativity with the quantum world. According to several quantum gravity models, spacetime is not smooth but granular. At the smallest scales, space becomes a network of discrete pieces, a quantum foam of interconnected loops and nodes. In these models, the Big Bang is not a singularity, but the moment when the quantum geometry of space rapidly reorganized. Before that moment, the universe might have existed in a state where time had no clear direction, where space was undefined, where cause and effect were not yet possible. The Big Bang becomes not an explosion, but the emergence of order from quantum chaos. In this ekpyrotic vision, the universe does not arise from nothing, but from interactions between structures larger and more complex than anything inside spacetime. Yet even this does not exhaust the possibilities. A different set of ideas comes from quantum gravity, which attempts to merge Einstein's relativity with the quantum world. According to several quantum gravity models, spacetime is not smooth but granular. At the smallest scales, space becomes a network of discrete pieces, a quantum foam of interconnected loops and nodes. In these models, the Big Bang is not a singularity, but the moment when the quantum geometry of space rapidly reorganized. Before that moment, the universe might have existed in a state where time had no clear direction, where space was undefined, where cause and effect were not yet possible. The Big Bang becomes not an explosion, but the emergence of order from quantum chaos.
One of the most mind-stretching versions of this idea comes from causal set theory. It proposes that spacetime is built from tiny, indivisible events linked by cause and effect. Reality is a growing network of moments, each adding a new point to the cosmic structure. According to this idea, the universe began when the first event came into being, and everything since then has been a continuous unfolding of new events. That means the Big Bang is simply the first link in an unimaginably large chain, an origin not in space, but in the creation of the very first moment. But as fascinating as these emerging theories are, they all face one shared challenge. They must explain why our universe has the precise values it does for its fundamental constants. If gravity were slightly stronger, stars would burn too quickly for life. If the electromagnetic force were slightly weaker, atoms would not hold together. If the masses of quarks had been slightly different, stable matter could not exist. This delicate balance prompts many scientists to ask, did the universe have to be this way? Or is it one of many universes, each with different constants, and we simply live in the one where life can evolve? This question leads back to the multiverse, but now with a deeper twist. Instead of imagining bubbles forming in endless inflation, some researchers propose that universes may branch from quantum processes. Every quantum event, every moment of probability may generate new universes with different outcomes. In one universe, a particle decays. In another, it does not. In one universe, a star forms. In another, it collapses. In one universe, life emerges. In another, it never appears. This is the many worlds interpretation of quantum mechanics, extended to cosmology. In this view, your universe is simply one path among countless quantum branches. You exist in one branch because that branch supports the physics needed for your existence. This is not science fiction. It is a serious proposal explored in research today. Other researchers take a different approach, arguing that the universe must be understood through symmetry. In physics, symmetry means that certain transformations, rotations, shifts, reflections do not change the equations. Symmetry is the language of nature. Every known force arises from a symmetry. Every particle emerges from a pattern. Perhaps then, the universe appeared because a deeper symmetry required it. In this picture, the origin of the universe is the moment when a perfect symmetry broke, creating the differences that form matter, energy, time, and space. Before that breaking, there existed a unified state beyond your ability to visualize. When the symmetry shattered, reality as you know it emerged. This idea echoes through every corner of physics. When water freezes, its symmetry changes. When particles gain mass through the Higgs field, a symmetry breaks. When the universe expands, symmetries evolve. The Big Bang may be the greatest symmetry breaking of all. At this point in your journey, you may feel that the possibilities are countless, and indeed they are. But this abundance of ideas is not a sign of confusion, it is a sign of progress. The more deeply you explore the origins of the universe, the more you discover how much there is still to know. The Big Bang is not a final answer. It is the beginning of a deeper and more astonishing mystery. The next frontier in cosmology will not simply measure the universe, it will attempt to explain why this universe, with these laws, exists at all. As you journey farther into these questions, you begin to see that the story of the universe is not merely about the past, but also about the future. The Big Bang defines how everything began, but the ultimate fate of the cosmos reveals just as much about its nature. The more you understand where the universe is heading, the more clues you uncover about what it truly is. One of the most astonishing discoveries of modern astronomy is that the expansion of the universe is speeding up. For many decades, scientists believed that gravity should slow the expansion over time, perhaps even causing it to reverse. But observations of distant exploding stars revealed something different. Galaxies are racing apart faster and faster. Whatever force drives this acceleration must be repulsive, must push space outward, must act against gravity itself. This mysterious influence is called dark energy. It fills all of space, yet you cannot detect it directly. You cannot hold it, measure it in a laboratory, or see it through a telescope. All you witness are its consequences, galaxies drifting apart like glowing embers carried by an invisible wind. But what is dark energy? Is it a property of space, a new field, a hidden force, or something far stranger? Some researchers believe dark energy is simply the energy of empty space, the same vacuum energy that might have sparked the Big Bang itself. If this is true, then the accelerating universe you see today is the long, slow echo of the same phenomenon that drove inflation in the earliest moments. The universe may be stretching now for the same reason it stretched then. Other scientists propose that dark energy could change over time. If it grows stronger, the expansion may accelerate so violently that galaxies, stars, planets, even atoms could be torn apart in a final cosmic catastrophe known as the Big Rip. In that scenario, space does not merely expand, it dissolves everything within it. Time would reach a final boundary, and the universe would end not in fire, not in ice, but in disintegration. But perhaps the opposite is true. Some theories propose that dark energy may weaken in the far future. If that happens, gravity might eventually regain control. Galaxies would slow, stop drifting apart, and begin collapsing inward. Over trillions of years, the cosmic structure could fold back on itself, leading to a final implosion called the Big Crunch. In that dramatic ending, the universe returns to a state similar to its beginning, immensely hot, dense, and compressed. But perhaps the opposite is true. Some theories propose that dark energy may weaken in the far future. If that happens, gravity might eventually regain control. Galaxies would slow, stop drifting apart, and begin collapsing inward. Over trillions of years, the cosmic structure could fold back on itself, leading to a final implosion called the Big Crunch. In that dramatic ending, the universe returns to a state similar to its beginning, immensely hot, dense, and compressed.
But now comes the twist. If the universe collapses to such a state, what happens next? Does it remain crushed forever, or does a new expansion begin? This question gives rise to a breathtaking idea, the cyclic universe. In this vision, the cosmos does not begin with a single Big Bang, but undergoes endless cycles of birth, growth, decay, and rebirth. After each collapse, the universe rebounds into a new expansion. Time becomes a series of epochs, each containing its own galaxies, its own stars, and perhaps its own forms of life. If this is true, then you are living not in the first universe, but in the latest chapter of an eternal cosmic story. Yet even this does not exhaust the possibilities. Another vision proposes a quiet ending. If dark energy remains constant, the universe will expand forever at an accelerating rate. Galaxies will drift beyond one another's horizons, leaving each isolated in darkness. Stars will burn out. Planets will freeze. Black holes will slowly evaporate into faint whispers of radiation. Over unimaginable stretches of time, the cosmos will fade into near-perfect emptiness. This is the Big Freeze, the slow fading of all structure into darkness. But even in this quiet final universe, mysteries remain. Some physicists propose that empty space may not be truly empty. Fluctuations in the quantum vacuum could create new universes spontaneously. In this vision, the end of one universe becomes the beginning of another, emerging from the quiet background like waves forming on the surface of a still ocean. In this grand picture, the Big Bang is not unique. It is one of countless eruptions within an eternal sea of cosmic possibility. But what about the deepest hidden layers of the universe, those beneath space-time itself? One idea gaining attention is that space does not exist as a smooth, continuous fabric. Instead, it consists of countless tiny units, like the pixels of a screen or the atoms of a crystal. These units could be connected by networks, forming a cosmic web far smaller than any particle you know. In this picture, the Big Bang represents the moment when the network expanded from a tiny cluster of nodes into a vast structure. Before that moment, the network may have been small, chaotic, or in a completely different state that does not resemble space as you understand it. This leads to another remarkable concept, emergence.
Many phenomena in nature emerge from simpler components. A flock of birds behaves like a single organism even though each bird follows simple rules. A human brain produces thoughts and consciousness even though each neuron acts without awareness. In the same way, space-time may emerge from the collective behavior of fundamental elements that are not themselves spatial. If this is true, then the Big Bang marks not the creation of physical matter, but the emergence of the very stage on which physics takes place. Before the Big Bang, there may have been no space to expand, no time to flow, no matter to form. Instead, there existed a deeper level of reality waiting to crystallize into the cosmos you see. This framework reshapes your understanding of the origin of the universe. Instead of asking what exploded, you begin to ask what changed. Instead of asking where did the universe begin, you ask what process made space-time possible. The Big Bang becomes not an explosion of matter, but the sudden appearance of geometry. Other researchers take inspiration from black hole physics. When matter collapses into a black hole, the information describing it appears to be stored on the event horizon, the boundary beyond which nothing escapes. If this is correct, then the birth of the universe could resemble the formation of a black hole in reverse. A white hole, a theoretical object that expels matter instead of absorbing it.
In this scenario, the Big Bang is the emergence of space-time from a white hole, releasing energy and particles into a new cosmic region. Perhaps this white hole formed from the collapse of a previous universe, linking cosmic epochs in a chain of transitions. Your universe may be the interior of a white hole formed long ago in a different parent cosmos. This idea remains speculative, but it illustrates how deeply the mystery of the Big Bang forces you to rethink everything you know. You might wonder whether signs of earlier universes could survive today. Some researchers propose that faint traces might appear in the cosmic microwave background, the afterglow of the primordial universe. They search for unusual circular patterns, temperature anomalies, or imprints that cannot be explained by standard cosmology. While the evidence remains uncertain, the possibility that your universe carries scars from earlier cycles continues to inspire new research. Other scientists look for clues in the fundamental constants of nature. Why do certain numbers, like the strength of gravity, the charge of the electron, or the mass of the Higgs particle, have precisely the values needed for stars, chemistry, and life? These numbers appear fine-tuned, as though they were selected from a vast menu of possibilities. If other universes exist with different constants, then perhaps you observe this universe precisely because it allows observers to exist. This is known as the anthropic principle, and while it does not provide a traditional explanation, it forces you to confront the relationship between life and the cosmos. Maybe the universe is not fine-tuned for life. Maybe life arises in universes that happen to have the right conditions. You begin to see that the mystery of existence is not limited to the Big Bang. At every step, from the formation of atoms to the structure of galaxies to the chemistry of your own body, the universe reveals astonishing precision. The very fact that you can ask these questions suggests that the cosmos has the ability to become self-aware. Now consider one more frontier, the simulation hypothesis. This idea proposes that the universe might be a computational structure created by an advanced intelligence. The Big Bang, in this view, becomes the initialization event, the moment the simulation began running. The cosmic microwave background might be the signature of a boundary condition. Quantum randomness might reflect the limits of computational resolution. And the speed of light might represent the maximum rate at which information can propagate within the system. Whether or not this idea is true, it challenges you to think differently. If the universe is a simulation, then reality is defined not by particles but by rules. Those rules would be the true physics. Across all these possibilities, one theme emerges. The origin of the universe is far more mysterious than a simple explosion.
The Big Bang is a window into a reality deeper than space, richer than matter, and older than time. You live inside a cosmic drama whose first act has not yet been fully understood. As you explore these ideas, remember that science is not a collection of final answers, but an ongoing journey. Each discovery opens new questions. Each question opens new worlds. And the greatest mystery of all is that the universe and its vastness has allowed you, a being made of stardust and thought, to look back across billions of years and ask, where did all of this begin? The truth may be more astonishing than anyone has yet imagined. The origin of the universe may involve higher dimensions, quantum information, mathematical structures, cosmic cycles, or principles not yet discovered. And as you continue learning, exploring, and questioning, you join the ancient tradition of humanity seeking to understand its place in the cosmos. The story of the Big Bang is still unfolding, and so are you.